This lecture is on section 4 of chapter 2. It's about measures of variations. So the first measure of variation that you can get from a data set is the range, which is the difference between the maximum entry and the minimum entry. Then we can talk about the variance and the standard deviations of the data set. So the variance of the data sets measures the spread between numbers or between entries between data point of the data set. So it will tell you how far away a data entries from the mean of the data sets, and also tell you how far away numbers or entries away from other numbers. So this lecture is on the measures of variations. This lecture is on the fourth sections of the chapter 2. It's about measures of variations. So the first measure of variation that you can find from the data set is a simple one, is the range, or the range is the difference between the maximum data entry and the minimum data entry. Then the next measures of variations is variance and the standard deviations. So variance is the measure that tell you the spread between data entries in a data set. So it will tell you how far away one entry from the mean. Third is tell you how far away all the data entries from each other. So it's measure the spread of the data set around the mean of the data set. So before we can find the variance and the standard deviations, we need to find the deviations of an entry X. So the deviations tell you the difference between that data entry and the mean of the mean of the data set. Okay. So once you have the deviations for each data point, data entry, then you can use the deviations of all the data entries to compute the variance of either the populations or the sample. So if you have a population data, then you can find the population variance, which is notated using sigma square, and it is equals to the sum of all the variance, the sum of all the deviations square divided by the size of the populations. Again, sigma is a lowercase of Greek letter and is called sigma. It's the population's variance. Population variance is sigma square, and it is the sum of the square of all the deviations and divided by the size of the populations. Let's take an example here. Consider that we have a population's data, and in this data we have 5 data points. Okay, and in each data point you can find the deviations of each data point using the formula finding the difference between each data point and the population mean. And as we know that we can find the population mean by adding all the entries and divided by the number of entries, and we should get 4.8 at the population mean. And from here, you can find the deviations of 2 by take 2 minus 4.8, 5 minus 4.8, 4 minus 4.8, 3 minus 4.8, and 10 minus 4.8. So in each entry, you can find the deviations of each entry. And you just take the result of this deviation and square it. So 2 minus 4.8 squared, 5 minus 4.8 squared, and so on and so forth. So we can find the square of each of these deviations, right? So you find the result of 2 minus 4.8 will give you negative 2.8 squared, you get 7.84. And then you do the same step for every single deviation, you just square it. And then the sum of all the square of the deviations is going to be 38.8. When you add all of this number together, you get 38.8. And from here, you can find this variance sigma square of this population data would be equal to the sum of all the square of the deviations and divided by n, which is the size of the sample, size of the size of the populations. And over here we have 38.8 divided by 5, which is equals to 7.76. So you just found a the variance of this data set, sigma square is 7.76. All right, so that's how you calculate the variance of the populations. And then the population standard deviations is gonna be just the square root of the variance. So the standard deviations will be to sigma equal to square root of sigma square, which is what you just found here, and equal to square root of the variance. So this is how you find the variance of the populations data. Take the square root of it, you get the standard deviations. So the standard deviations here is always positive because it's the square root of a positive number. And then if you have sample data instead of a population data, then you can calculate the variance and also the standard deviations of the sample in a very similar way, except you will use X bar, right? Because X bar is a sample mean. Instead of mu is a population mean, and you divide the sum of the square of the deviations by n minus 1, where n is the sample size. The reason why you subtract 1 from n, because when you look at the sample data, you losing 1 degree of freedom. That means when you have just a sample, not a population, not a census, that means you can always try to find the mean of the sample. You have one available data, which is the mean of the sample. So that's why the degree, you're losing 1 degree of freedom, and that's the reason why you have to subtract 1 from n, which is 1 from the sample size. And again, if you want to find a standard deviation, you just need to take the square root of the variance of the sample. And in sample data, the variance is denoted using S squared, and the standard deviations is denoted using S. So you can compare that. In populations, you use sigma square as a variance, and sigma is the standard deviations, versus in sample data, you use S as the standard deviation and S squared as the variance. So here's some observations about standard deviations. First, the standard deviation sigma, right, has the same unit as the data set. For example, if the data set has a unit of minutes, then the standard deviation also has the same units of minute. So the standard deviations measures the variations of the data set about the mean. So it will tell you, because based on the formula that we use to find the variance and the standard deviation, you can see that we find the variations of the data set about the mean. So that's why we find the difference between each data point with the mean, and we square them and we take the square root of the whole thing. So the standard deviations or the variance measures the variations of the data set around the mean. That says standard deviation is always positive, right? Always non-negative, greater than or equals to 0. If the standard deviation equals to 0, sigma equals to 0, that just means there's no variation at all. Thus, all the entries have the same value. If you don't have any variations between data entries, then the standard deviations is very low and sometimes it's 0 if all the entries have the same value. And as the entries get farther and farther away from the mean, that is, it's more spread out, then the value of standard deviations, sigma, increases. You can imagine that. So if I have data, I have a set of data that is around, that is like very, this is each dots here represent for data points, right? It's around away from around the mean, right? So this is the mean of it. That means my standard deviation is not so big, right? Because everything seems to cluster around each other. Versus if I have a different data set where I have my data point are kind of spread out. And then if I want to, this is more or less like the mean of the data set is in the middle point here. As you can see that the data set is more spread out. And if I want to find, and then if this is sigma, right? If I find this is the standard deviation of this data set, I set sigma 2, and this is sigma 1, then clearly if you're using the same unit, then sigma 2 should be greater than sigma 1. Because in this data, my data points are more spread out around the mean compared to this data. All right, and I posted the video that help you find the mean and the variance and the standard deviations of a quantitative data set using Google spreadsheet. Well, let's look at the next example. So this example provides annual salaries for entry-level architects in Denver and in Los Angeles. So in Denver, we collected 10, right? 2 data sets, one from Denver and one from Los Angeles. And clearly that this is a sample. This is a sample data set, right? Because there should be more than 10 architects in Denver and in Los Angeles. Now you can see that in the first questions here, they ask what is the average annual salary for entry-level architects in Denver. So you just need to find the mean of this data set. Okay, you want to use 2 decimal places. And the next question is, what is the average annual salary for entry-level architects in Los Angeles? So again, you want to find the mean of this data set. And then what is the variance for the data, for the Denver, Colorado data? So you want to find, let's say, if I have the first mean, so we'll say X bar 1, right? X bar 2. So X bar 1 is the mean of the Denver data set. X bar 2 is the mean of the Los Angeles data set. And the variance of Denver, I call it variance. So you have S squared equals 2. And then the standard deviations of the for the Denver, so that should be S. And I say S1 and S1 here. And the last question is, what is the standard deviations for the Los Angeles data? So standard deviation, it should be S2. Standard deviation is not variance. So I enter this two data set into a Google spreadsheet, and here's the data for entry-level architects in Denver, and this is data from Los Angeles. And so you can see I can calculate the mean of this Denver data set using the average formula, right, from B41 to B52. I can find the variance of the data set too using the variance for a sample VARA. This is the variance of the sample of this data set from B41 to B52. And also I can find the standard deviations for a sample because this is the sample data. I use this functions and deviations A for the sample from B41 to B52. So similarly, I can find the mean, the variance, and the standard deviations for the Los Angeles data set. And again, this is a sample data set, so you have to find the variations and the variance and the standard deviation using the correct formula. All right. So I found this is the mean, the variance, and the standard deviations of the data set, of these two data sets here. All right, so I answer all of these questions here. As you can see, x bar 1, x bar 2, s1 square, s1, and s2, right? These are the two standard deviation for the two data sets here, right here. You can see that they are slightly different. They're only like 0.02, 0.2 difference between the two. Thus the variations, standard deviations, and the mean are quite different here. So the mean for the Denver data set is 46, and the mean for the Los Angeles data is 52.88. So the mean are quite different, like 4,000 difference. But the standard deviations here is only 0.2 difference compared with each other. So once that we know how to find standard deviations, how can we interpret standard deviations in the context of your data? So the first rule that we can use in order to interpret the standard deviation is called Empirical Rule. It's 68, 95, and 99.7 rule. So this rule says, for data sets with distribution that approximately symmetric and bell-shaped, the standard deviation has the following characteristic. First, about 68% of the data lie within one standard deviations about the mean. Second, about 95% of the data lie within two standard deviations about the mean. And lastly, about 99.7% of the data lie within three standard deviations of the mean. And we're saying that the majority of the data will lie within one or two standard deviations of the data sets, right? Because if you go to two standard deviation away from the mean, it's already captured 95% of the data. All right, let's illustrate this rule. Again, if you have a bell-shaped curve distributions, this is approximately symmetric and bell-shaped curve distributions. And in the middle, you have the mean of the data sets. If I'm looking at the population data set, so this is the mean. And if you go to one standard deviations away from the right, I have the mu plus sigma. And you have two standard deviations, and then this is three standard deviations. Okay. These are the number of standard deviations away from the mean from the right, on the right of the distributions. And then I go to the left, mu minus sigma, mu minus 2 sigma. And then the last one, mu minus 3 sigma. All right, according to the rule, we know that around 68% of the data set lies within the one standard deviations away from the mean. So as you can imagine that your data points are distributed here, everywhere here, right? So this is the distributions of the data set, and the distribution of this data set is bell-shaped distributions. All right, so 68% of the data sets lie within one standard deviations away from the mean. Okay, and the next rule is about 95% of the data set would lie within two standard deviations away from the mean. So from here to here, you're capturing 98%, 95% of the data set. In this area here, you're capturing 95% of the data set. Okay, you're observing 98% of all the data points. And then the last rule is you will see that you will see 99.7% of the data set in between 3 standard deviations away from the mean. So this is 99.7%. Okay. Again, you can only use this rule when your data set is symmetric distributions and also bell-shaped curve distributions. And as you can see that if you go further away from the data sets, more than 3 standard deviations from the on the right or on the left, you will rarely see any observations in these two tails here. But you mostly you will see all the observations in between among 2 or 3 standard deviations away from the mean. Okay. And all the observations that you're observing in these two tails, on the right tail and on the left tail, they are considered as outliers or unusual observations of the data set. Okay, so let's look at the example number 9. So I say the mean speed of a sample of 75 vehicles along a stretch of a highway is 67 miles per hour, with a standard deviations of 4 miles per hour. Okay. First, estimate the percent of vehicles whose speeds are in between 63 and 71 miles per hour. Assume that the data set has a bell-shaped distributions. So if your data set has a bell-shaped distribution, that means I can use the empirical rule in order to estimate the percent of vehicles whose speeds in between 63 and 71 miles. So let's draw a picture to see what's going on here. So we have a bell-shaped distributions, okay? And then we know that the mean of the sample, so this is a sample data. And the mean of the sample is 67. So 67 is a mean, is the center of the data. 67 here. And the standard deviations. So X bar is 67. S is 4. Okay. So then you know that using the empirical rule, about 75% of the data sets lie within one standard deviation away from the mean. So then if one standard deviation away from the mean on the right would be 67 plus 4 would be 71. And is x bar minus s. Just one s, and this is x bar plus one s. Okay. And you observing 68% of the data set. So using the empirical rule, we know that 68% of the sample are between 63 miles per hour and 71 miles per hour. Okay, so as we know that, which is, then we know, oh, this is 68% of the sample, right, of the vehicles will have the speed in between 63 miles per hour and 71 miles per hour using the empirical rule. And then the next question is estimate the number of the vehicles whose speeds are in between 63 and 71. So about 68% of the samples, and the total of the sample is 75. So the number of vehicles will be equals to 68%, right? Multiply to 75, which is equal to 0.68 times 75, which is equals to 51. So there's 51 vehicles whose speeds that are in between 68 miles per hour and 71 miles per hour in this situation. Theorem. You can use this theorem, or you can use this rule to any of the data set. Your data set doesn't have to be symmetric, doesn't have to be a bell-shaped curve data set. You can use this rule to any of the data sets. So this rule says, the Chebyshev theorem, say the portions of any data set, right? Any data set lie within k standard deviation where k is strictly greater than 1. Of the mean is at least 1 minus 1 over k squared. So portions, the percentage of any of the data set that lie within k standard deviations is at least 1 minus 1 over k squared. So for an example, for k is strictly greater than 1. If k equals to 2, then you have 1 minus 1 square equals 1 minus 2 square. So this is k. Equals to 3 over 4. That means you have 75% of the data set lie within 2 standard deviations of the mean. Okay, 75% lie within 2 standard deviations of the mean at least. If k equals to 3, then you have at least 88.9% of the data that lie within 3 standard deviations of the mean. So you can use this theorem for any data set. If you don't know the distribution of the data set, you can always use this theorem. And compared to the empirical rule, you can always, you can only use the empirical rule when your data is symmetric and bell-shaped distributions. You can see slightly the difference, right? So in Chebyshev rule, only 75% of the data lie within 2 standard deviation compared to empirical rule, that's 95% of the data lie within 2 standard deviations, and so on and so forth. So you have a nicer and better estimations of the data set of the proportions of the data sets lie within the number of standard deviations if you have a bell-shaped curve. Compared to Chebyshev, you can use, but the one advantage of the Chebyshev theorem is you can use this theorem to any data set. All right, so let's look at example number 10. So it's saying you're conducting a survey on the number of pets per household in your regions. From a sample of n equals 40, the mean number of pets per household is 2 pets. So the mean is 2. The standard deviation is 1. Using Chebyshev theorem, determine at least how many of the households have from 0 to 4 pets. So looking at these examples here, I know n equals 40, which is the sample size. I know the mean of the sample is x bar equals to 2. I know the standard deviations is 1. Okay, and I want to estimate how many households that have number of pets in between 0 and 4. So x is the number of pets. Right, of each household. Again, we do not have any information about the distributions of this sample. It's not symmetric, not sure, it's not even, I'm not sure if it's symmetric or not. I'm not sure it's a skew right, skew left. It can be any distributions. So that's the reason why we can use Chebyshev's theorem to estimate at least how many households that have from 0 to 4 pets. Okay, so using Chebyshev theorem, we know that the mean is 2. So let's see, this is a mean, x bar is 2, and here is 4, and here is 0, right? So this is maybe this is the distributions of it, and you need to estimate what is the percentage, right? What is the number of the household that in between 0 and 4? And we can notice that 4 is 2 standard deviations away from the mean, x plus 2s, right? 4 is equals to 2 plus 2 times 1. So it's 2 standard deviation away from the mean. Also 0. 0 is also 2 standard deviations away from the mean on the left. So it's x bar minus 2s. Because you have x bar is 2 minus 2 times 1 is 0, right? So you can see that, okay, now we know that k, number of standard deviation in this situations, in this problem is 2. So k equals 2, that means you have at least, using the Chebyshev theorem, you have at least 75% of the sample, right? Lie within 2 standard deviations. You have, using Chebyshev theorem, at least you have 75% of the households. Of the households that would have from 0 to 4 pets. Okay, so we know that it's 75% and 70, so that means there's the number of households that have 0 to 4 pets is 0.75 times 40 equals to 30. So 30 households should be the final answer for these questions. Okay, using Chebyshev rule. So you want to use the Chebyshev rule right here to estimate the number of the households in this sample that have from 0 to 4 pets. And we can use 0 to 4 as the number of standard deviation away from the mean, and we determine that it's going to be, so k is just going to be 2, and if k is 2, then 75% of the households we have between 0 to 4 pets. All right, so we learn, in these sections, we learn some measures of variations of the data sets. More importantly, we learn how to distinguish between the variance and standard deviations. We learn how to calculate those variance and the standard deviations for the population and for the sample data. They are very similar, except that on the sample data, you have to subtract 1 from the sample size because it's 1 degree of freedom less. All right. And then you learn how to use Google spreadsheets in order to find the average, the mean, and the variance and deviations of any of the data sets. Keep in mind that you want to make sure that you know if it's a sample data set or is this a population data set, so that you can use the correct functions. All right, and then you learn the empirical rule and Chebyshev theorem. Those are 2 rules that help you interpret the standard deviations of the data sets. Again, in order to use the empirical rule, your data set has to have the distributions of symmetric and bell-shaped distributions. Versus if you don't have any information about the distribution of the sample, you can always use the Chebyshev rule. And Chebyshev rule is a bit weaker compared to the empirical rule, but it has an advantage of that you can use this rule to any of the data sets.